of the avoided crossing type, which possibly can happen in graphene with impurities. The possible rearrangement of the spectrum, as it was called at that time, was proposed as an effect in solid state physics by Arnold Kosevich long time ago. At that time, he dealt with the acoustic phonons, and he found from his theoretical point of view that in the presence of heavy substitutional impurities in normal three-dimensional dielectrics, we will have something strange happening with the dispersion relation of acoustic phonons. And then he showed, and he mentioned about this in his book, that this is a special kind of spectrum rearrangement. Why I would like to call it avoided crossing type? Because we have the dispersion initial of the system without impurities, and we have some impurities that can lead to the appearance of the well-defined, sharp impurity resonances, which have certain frequency. And then when we increase the amount of impurities, we see that the dispersion of acoustic phonons is split into two branches. So we have two frequencies which can be related to each wave vector. In this case, the lower branch stops just below the resonance frequency, and we have a new limiting frequency, but upper branch doesn't go up to this limiting frequency, it smears out. The question is, can we have something like this in the electronic spectrum of graphene? And indeed, after the presence of impurities. Let's take maybe before a more close look at this band structure transformation. Again, I would like to stress that we have a lower branch, which disappears when we are approaching the resonance frequency, around which we have something that is usually called concentration broadening, where we have localized states without any definite systematics. We have a quasi-gap, which is filled by the localized states that are based on the pairs of impurities when the concentration is small, and we have another one, upper branch. So let's consider graphene and its electronic spectrum. Our Hamiltonian will consist of the initial, which corresponds to the clean graphene and includes hoppings between nearest neighbors. As usual, here alpha and beta enumerate sublattices, and M are radii vectores of lattice cells. And impurity part. Impurity part we will take in a interesting form of Fano impurities, so that each impurity, by supposition, will introduce a new level, but this level is hybridized by the hopping with the p orbitals of the graphene sheet. So we have hopping from the carbon atoms to this new, probably we are talking about just an atom that is laying on the graphene sheet and backwards. And here, this eta takes a value of unity with the probability of C, which is the concentration of impurities, and 0 when the impurity is absent. We can write down the Green's function of our system when we have a single isolated impurity. Then follows simple algebra, and we can express the diagonal element of the Green's function of the system at the impurity level using the host Green's function. And by the way, the diagonal element of the host Green function in the side representation. This is by definition the host Green function. And it is well known that in graphene, the diagonal element takes this form when we are located in energy close to the Dirac point. When we'll look more closely to the obtained relation, we can figure out easily that for local density of states at the impurity level, we will have a Lorentzian. We should demand that we will have a sharp resonance. And this means that the broadening of this resonance should be less than distance from the nearest one whole singularity in the whole spectrum. Basically, in this case, this is the Dirac point. Therefore, after some redefinitions, we get the following condition that should be satisfied for resonance to be really sharp. This means that the damping of the resonance should be much less than the resonance energy. Indeed, we count energies from the Dirac point. And this small parameter will be used throughout our consideration. And then I would like to say that here we have, as a small parameter, the a bit renormalized hopping integral between carbon, basically the p orbital of carbon, and our new impurity level. So this hopping should be small. This denominator is just small renormalization. And you can see that if this initial hopping integral that comes from the Hamiltonian is small, this is nearly unity, and these two values are equivalent. So, according to the single impurity problem, we got a condition for the existence of sharp impurity resonance. Now we want to increase the amount of impurities, and we'll consider a lot of impurities which are distributed absolutely at random with certain probability in our system and have same properties. So let's say it will be atoms scattered around the graphene sheet. In this case, we can use the usual trick and eliminate the wave function on the impurity level so that we will reformulate the perturbation and then write down such a Hamiltonian with same occupancy number. To treat our problem, we will try to calculate the average over possible impurity distributions, Green's function of our disordered system. And we'll do this by finding a corresponding approximation to the self-energy, which will be done according to the modified propagator approximation. And that will look like this in for the case of our final impurity mode. Let's have a closer look at the spectrum. First of all, we will seek for those domains in the resulting spectrum where the renormalized energy, which is determined like a difference between energy and the real part of the mass operator, will be larger than its damping, which follows from the same value from the mass operator. In this case, we can try to find renormalized dispersion relation, which stems from the dispersion relation of the graphene without impurities. So, after examining this condition, we can easily figure out that for states of electron, we should have this condition fulfilled in order to have itinerant states, so that this one equality is not violated. After that, we can approximate our expression for the renormalized energy a bit around the energy of the resonance, and then find the dispersion relation for the itinerant state. Immediately, we see that we have two direct points. One of them is the old one, but which is shifted away from the energy of impurity resonance. And second one, let's call it nodal point. This will be an extra direct point in the system. New one, before it was not in the spectrum at all. So, because actually in graphene we have two direct points in the brilliant zone, it means that each direct point will be double. After that, we can see that there is some distance from the new direct point to the resonance, and can find that low impurity concentration expression free. And we also have the concentration broadening of the resonance. So spectrum will be rearranged, or spectrum will be transformed when distance from the new direct point to the resonance energy will exceed the broadening of the resonance energy. Otherwise, we will not see it. That means that we can pinpoint some critical concentration of impurity at which we will have totally different kind of the electronic spectrum. And for this expression, we had to assume that C is much less than some special concentration, C star, and we should know that critical concentration of impurities is much less than this special C star. We'll talk about it a bit later. So what we have as a brief sketch of the band structure transformation graphene. In the case of impurities, we have that by dashed lines we plotted here the initial dispersion of electrons. We have the energy of impurity resonance. But actually, when the concentration of impurities exceed the critical one, we have a broad area around the resonance where states should be localized and branches of new dispersion. I should stress that we have a new Dirac point in the system. By the way, these branches of electronic dispersion are not going up to the boundaries of the Brillouin zone, but disappear at some maximum value of the wave vector. Actually, at the same maximum value, both of them. As our new dispersion branches are approaching the concentration broadening area at the impurity resonance energy. So if you look at the spectral function, then spectral function at these values of K vector we just smeared down. Let me just mention some interesting things. First of all, the maximum value of the K vector is proportional to the square root of the impurity concentration. So it corresponds to the mean distance between impurities. Such physical meaning is maybe obvious. And then we should state that the broadening, concentration broadening of the impurity resonance always exceeds the concentration broadening of the resonance which we had for a single impurity in a system. So when we add impurities, the damping at the resonance energy only increases. And this corresponds to concentration that are larger than the critical one. Let's look at the Fermi velocity near the new Dirac point. And it is easy to see that when concentrations are less than mentioned above C star, the Dirac velocity is significantly reduced for small impurity concentrations. Let's take a look what we have when concentration of impurities is exceeding the critical concentration and is less than C star. We have a relatively narrow broadening of the impurity resonance energy. We have a second new one, Dirac point in the spectrum, but with significantly reduced Fermi velocity. And we have, of course, old one, Dirac point, which is shifted from its initial position. Here again, dotted lines, this is the electron dispersion in the amplitude crystal. Well, and that's it. So here we have such a continuation with, well, anomalous dispersion. When we increase concentration more, what we'll have? We will have that the distance between new Dirac point and impurity resonance is increasing like square root of concentration. And it is much larger than the broadening of the impurity resonance here, delta, if you remember our small parameter of the system. And Fermi velocity is leading to 1/2 of its initial value. And also we can point a third one, special concentration, when the broadening of the impurity resonance is larger than the energy of the impurity resonance. So what we will have? The concentrations that are larger than C star, we have that area of concentration broadening of the impurity resonance becomes much wider, and the mu velocity increases. Here we compare two main parameters: the broadening of the impurity resonance and the distance from impurity resonance to new Dirac point. And we see that initially the broadening, formally at least, initially the broadening of the impurity resonance exceeds the distance to the new Dirac point, so it doesn't exist, but then it dominates. And at the second stage, when concentration is larger than C star, we have that they are obeying the same law in their dependence on concentration, but always the distance to the impurity new Dirac point is much larger. And finally, if we exceed the third concentration, there is a new regime, because concentration broadening of the impurity resonance becomes much larger than the resonance energy, and the symmetry of the spectrum is to some extent restored. So particle-hole symmetry, which was violated initially by the presence of impurities, at least approximately, is restored, and we have same dispersion below and above zero energy, where initially Dirac point was located. Let us take a look at the dispersion in 3D. So here, two cones represent the initial dispersion relation of graphene, and then after adding a concentration of impurities that exceeds the critical one, we have spectrum that have two Dirac points instead of one, and while these cones are removed and shifted far away from each other, we have a kind of symbols that appear and are just fading away with increasing the wave vector. Well, I'm done. Thank you. Thank you for attention. I can read this, or you can read this.
Yes, thank you very much.
My question is the following. Is your result depend on distribution of impurities over the surface of graphene?
Strictly speaking, it depends, of course. When we will have a certain strong correlation in the deposited atoms, we will have slightly different result. But I know about the numerical experiments that show that if correlation is moderate, nearly nothing changes.
It's possible regular position of impurities on the surface.
No, it's not the same. Answer will be totally different, and regular distribution of impurities is what it's better to say, is absolutely wrong solution to the impurity problem. So we will have just superlatives. We will not have localized states, and our systematics will look absolutely different. So this is not the right approach. But the answer is that if you will have some liquid-like correlation between impurities, probably results will not change much.
Well, I would like to ask, from what observation the right part, impurity part in Hamiltonian in such form which you present?
From what?
From what motivation do you take the impurity part in Hamiltonian?
Yeah. So motivation is, first of all, yeah, there are two motivations. The first motivation is this is a kind of perturbation that corresponds to the well-known Fano impurity model, which was used frequently for the impurity centers in different systems. Second motivation, this Fano impurity model is well suited for the add atoms on graphene, because add atoms usually represent an additional level.
And what is this dependence in such form?
When?
Yeah.
Always. So
In form, impurity part.
this is our Hamiltonian. I suppose that here no questions arise. Each impurity has some new level,
Okay.
and hopping to the host. When we will exclude the wave function at the impurity level, we will have the perturbation with a pole. This is just a trick which is frequent, always used for Fano impurities for decades.
Okay.
And this also gives the third one motivation, because when we have the impurity perturbation with a pole, we can expect a strong renormalization of the dispersion relation. Simply because we here have, and then can have a large effect on the outcome of the spectrum in the disordered system, like in the papers.
Okay, excuse me, Eric, I will have the question, please.
Is it my turn?
Yeah.
Oh, thank you. First, I want to say which you know, because you have been here in Stockholm, that there is a large activity in Stockholm around graphene in many theoretical investigations by people at Nordita, Balatsky, and others. And I'm not at all such an expert. So we have in Stockholm much better experts. I'd like to ask, maybe it's a stupid question, but on the same page 8 as where you were before in the Green's function, this one, I guess this one. Is it possible to get something very different, qualitatively different, when you average the Green's function that it doesn't look like a Green's function at all. Is this possible?
I don't understand what you are meaning.
Well, you have there the average of 1 over the energy minus h, right?
Yeah.
And you are looking at this, that there is, it more or less looks the same. There's only a little change, the sigma epsilon, no? That's the only change.
Yeah.
Yeah. Can you have situations where when you average something, you get something which looks very different? Not at all a pole. And the pole changes
in
to
some
something
sense,
very-
yes. So when we average the Green function of the disordered system, the translational invariance is restored. So then we can introduce a wave vector as a legit variable to count our states. And then we can use approximate solution and to put on each side of the lattice something that is usually called the coherent potential, which is complex. And its imaginary part translate the information that our system was disordered. So actually it is not translationally invariant. So, but this is a usually widely used approximation to treat our single electron problem. Otherwise, indeed, we should take it to computer cluster and calculate, but on paper with a pen, it's probably impossible. Absolutely. So there, if we will put a bit different question, we can say indeed that average Green's function lost some information on the system. But probably there is no other choices working with it. And probably we can calculate something different. So let's say Green's function with the first site occupied by impurity and so on. And draw our decisions.
Okay. Thank you. Again.
Yeah, thank you.
It was my pleasure.
Okay.